So you're working with AI and you've got all these different models to choose from. How in the world do you pick the right one? The best one? Well, today we're going to break down exactly how you can select the perfect AI model for pretty much any task you can think of. And to make this really hit home, let's raise the stakes a lot. Imagine we're working with the breast cancer Wisconsin dataset. We've got a whole bunch of AI models ready to go, and it's our job to pick the one we trust to tell the difference between a benign and a malignant tumor. This is a life or death distinction. How do we make that call with real confidence? Here's the first and most fundamental truth. There is no magic bullet. There's no one-size-fits-all model that just works for everything. A model that's an absolute genius at finding spam emails might be completely useless for medical diagnoses. And that's why choosing a model isn't just a simple step. It's this whole rigorous process of testing and experimentation. Now, the single biggest obstacle we face in this whole process is a really sneaky and dangerous pitfall. It's something every data scientist has to learn how to spot and navigate. It's called the overfitting trap. This trap really has two sides to it. On one side, a model can underfit. That means it's just too simple and it completely misses the important patterns in the data. But on the other side, a model can overfit, and this is where it gets tricky. It becomes so complex that it basically memorizes the training data, including all the random noise. It's kind of like a student who memorizes every single answer for the practice test, but then completely bombs the final exam because they can't handle any new questions. Let's break that down a bit. When a model is underfitting, we say it has high bias. You can think of bias as a kind of stubbornness. A model with high bias has these really strong but wrong assumptions about the data. So no matter what you feed it, it's just going to be consistently wrong in the same way. And on the flip side, overfitting gives us what we call high variance. You can think of this as a model that's super jumpy and unstable. If you just change the training data a tiny little bit, its predictions will swing all over the place. It's just not reliable because it's chasing the random noise instead of the actual underlying signal. So, how do we dodge this trap, right? How can we be sure that our model is actually going to perform well out in the real world on data it's never seen before? Well, it turns out we need a much smarter way to test it. And this brings us to this brilliant technique called K-fold cross-validation. Instead of just splitting our data once into a training set and a test set, we divide our data into, say, 5 or 10 different groups, which we call folds. Then, we train the model on all but one of those folds and test it on the one we left out. And we just repeat this process over and over, letting each fold get a turn to be the test set. By averaging all of those results, we get a much more stable and reliable estimate of how our model will actually perform. And hey, here's a quick pro tip for you. For data sets where the classes aren't balanced, like in our cancer example, where malignant tumors are hopefully much rarer than benign ones, there's an even better version called stratified K-fold. It just makes sure that each little fold has the same percentage of each class as the full data set. Pretty clever, right? Okay, so we've used cross-validation, and now we've got these really solid performance scores for a few different models. But, just staring at a bunch of numbers can make it hard to really compare them. What we need is a way to see the performance, to visualize it. How do we really see the trade-offs that each model is making? Is one model great at catching the positives, but maybe has a lot of false alarms? Is another one more conservative? How can we see that at a glance? Well, the answer is an amazing tool called the Receiver Operating Characteristic Curve, or just ROC curve for short. It's so powerful because it shows us the model's entire performance in one simple graph by plotting its successes against its mistakes. Let's actually build one in our heads. The vertical axis, the y-axis, that's the true positive rate. This is all the good stuff. In our cancer example, this is the percentage of actual malignant tumors that our model correctly identified. We want this number to be as high as possible, obviously. Now, the horizontal axis, the x-axis, this represents the false positive rate. These are the mistakes, the false alarms. This is the percentage of perfectly healthy, benign tumors that our model incorrectly flagged as malignant. And of course, we want this number to be as low as we can get it. So how do you read one of these things? It's pretty intuitive. The absolute perfect model would be a single point way up in the top left corner. That's a 100% true positive rate with a 0% false positive rate. That diagonal line cutting across the middle, that's just random guessing. So any model whose curve dips below that line is literally worse than just flipping a coin. Now, comparing a bunch of different curves can still be a little messy. Wouldn't it be great if we could just boil down the entire performance of each model into one simple, easy-to-compare number? Well, we can. We use a metric called the area under the curve, or AUC. It's exactly what it sounds like. It measures the total area underneath that ROC curve. A perfect model gets a score of 1.0. A random guess gets a 0.5. So the higher the AUC, the better the model is at its job overall. So now we've got our models, we've got our AUC scores, we can rank them. But here's where it gets really important. The numbers don't make the final decision for us. We do. Because the best model always depends on which kind of mistake we're more willing to live with. Let's go right back to our main question. In cancer detection, what has the higher cost? Is it a false positive, a false alarm that causes a patient a lot of stress and leads to more tests? Or is it a false negative, where we miss a malignant tumor completely?
This is where we have to choose a specific operating point, a threshold on our model's ROC curve. For instance, if we were in a situation where false alarms were incredibly costly, we might choose point A. We get a very low false positive rate, even if it means we miss a few true positives. But for cancer detection, the cost of missing a positive diagnosis is just way too high. We would almost certainly choose something like point C, where we maximize our true positives, even if that means we have to deal with a few more false alarms.
All right, let's wrap this all up. So what did we learn? First, there is no single best model for every problem. You've always got to watch out for that overfitting and underfitting trap, that battle between bias and variance. To get a real sense of performance, K-fold cross-validation is your best friend. Then you can use tools like the ROC curve and the AUC score to visualize and compare your models. But, and this is the big one, the final choice always comes down to the real-world cost of that model's mistakes. And that really leaves us with one last critical question to think about. We now know how to pick the best model from a group of candidates. But when does that best model actually cross the line from just being a cool academic exercise to being something we can actually deploy and trust with people's lives? Now that's a question that goes way beyond the data.